In this video, we will be looking at section 6.1, which covers sinusoidal graphs. So we're going to start by talking about periodic functions. And a periodic function is one that repeats. So we can define that as a periodic function is a function for which a specific horizontal shift p results in the original function. Meaning if you shift the entire function over whatever this p is, it's going to land on itself. So you can say f of x plus p equals f of x for all values of x. The definition of period is going to be the smallest horizontal shift p that's positive, such that f of x plus p equals f of x. So the shortest distance you have to move for the function to land on itself. Now when we're talking about periodic functions, we're going to be focusing, at least in this section, on sine and cosine. So I want to show you how these are obtained. So I'm going to show you a neat little Desmos. It's a figure, I guess. An animation, that's the one I'm going for. So what I have here is a unit circle. So the radius on this guy is 1. We're going to start with the sine animation. So remember, on the unit circle, sine is going to be the y value. So whatever y value we are at on this is going to be our function value for sine. So notice that whatever height we are away from the x-axis is going to be the height on our actual function. So we are graphing sine right now. So you'll notice that sine starts at the origin, goes up at its maximum value right here. That happens at pi over 2 radians, which is 90 degrees, and that reaches a height of 1. It comes back down until we are at an angle of pi, which would be 180 degrees, and we are on the x-axis there, so we have a value of 0. We go down until we're at -1 at an angle of 3 pi over 2, and we come back to 2 pi. And then we start oscillating again. So we get this idea of the periodic function because it's repeating every 2 pi, starting on the x-axis and going up, coming down, hit the x-axis, going up, coming down, hit the x-axis. So it's repeating every 2 pi. Let's see what the sine function the cosine function looks like. On the unit circle, the cosine is equal to the x value. So whatever x value we are at is going to be the function value here. And you can see it marked with orange dotted lines, that however far we are away from the y-axis, that's going to be our x distance. And that's what we're measuring in our cosine function. So this one is starting up at the very top because our x value starts at 1. So we go from 1 and then at pi over 2, that's 90 degrees. Our x value is 0 because we haven't moved left or right away from the y-axis. Then we go down until we hit -1 and back to 0 and back to 1. So this also has a period of 2 pi. It's just a matter of where we're starting. So I really like that animation because it kind of shows where this is all coming from. So a couple notes about the sine and cosine graphs. The domain of sine and cosine are all real numbers. So you can plug any number into them and you'll get out a value. As you probably noticed from the Desmos animation, the range was -1 to +1 because we could go as low as -1 and as high as +1s. We call these graphs sinusoidal. And then the period is 2 pi for both of them. So we saw that the graph repeated itself every 2 pi. There are a couple of things I want to point out about sine and cosine, and one of them is that I want you to look at the negative angle identities. So we want to see what sort of symmetry there is with our sine and cosine graph. So the first graph here that we're looking at is sine, You can tell because we start at the origin and go up. Now, this isn't a reflection over the y-axis. It doesn't land on itself that way. It's not a reflection over the x-axis. It doesn't land on itself that way. But if you flip it both ways, if you flip it horizontally, then vertically, or vice versa, then it will land on itself. We also say that this is symmetry, or it's symmetric through the origin. All right, so for example, if we take this point up here, pi over 2 comma 1, we flip it over the y-axis and then over the x-axis, we land on that point there. That gives us the fact that the sine of negative theta is equal to the opposite of the sine of theta. So for example, we were using this point and how it ended up here. So if our theta, our angle, is pi over 2, then the sine of negative pi over 2, we got to be negative 1, is the opposite of the sine of the original angle. The sine of the original angle was 1, put a negative in front of it, you get negative. The cosine graph, on the other hand, this one is symmetric over the y-axis. If you were to flip it horizontally, it would land on itself. So this is symmetric over the y-axis. And what that means is the cosine of the negative angle is equal to the cosine of the positive angle. So if we pick an angle like pi over 2, the cosine of negative pi over 2 will be the same. If we're looking at the cosine of 2 pi, it's the same as the cosine of negative 2 pi. What that means about these functions is that sine is an odd function and cosine is an even function. Those are some definitions that we saw a few chapters ago. These identities can be really useful, so I just wanted you to have those as something to use. Next up, we're going to look at transforming sine and cosine. So we're going to start by sketching a graph of y equals 2 times the sine of theta. So I have some grids here. I didn't label the y-axis, it doesn't look like. So I will let it go up to, we'll say each little line is a half. We have 1, 2, -1, -2. I'm going to start by graphing just normal sine. Sine of 0 is 0, the sine of pi over 2 is 1, sine of pi is 0, 3 pi over 2 is -1. So we're getting this beautiful sinusoidal curve, assuming I could draw them, and it continues on. So that is the graph of y equals the sine of theta. But I want to graph y equals 2 times the sine of theta. Do you remember what that 2 does out front? That is a vertical stretch by a factor of 2. So that means I can take all of my y values and multiply them by 2. If my y value is 0, 2 times 0 is 0, so that it stays there. When my y value is 1, I multiply it by 2. 0, -2, 0. So we're getting the same look of a curve, it's just stretched vertically. So instead of going between, there we go, between -1 and +1, we're going between -2 and +2. Next up, we're going to graph y equals -3 times the sine of theta. So we still see that stretch factor, this time it's 3, but there's also a negative. So we're going to take the normal sine graph. There's a vertical stretch by a factor of 3, but then that makes a reflection. That one's a vertical reflection. So what I'll do is I'll first graph y equals 3 times the sine of theta, because I already had sine of theta over here. So we'll go 1, 2, 3 this time so that fits. So if I'm multiplying all my y values by 3, then I'll get 0, at pi over 2 will be at 3, pi will be at 0, 3 pi over 2 will be at -3, and then 0 again. So I'm getting this graph by taking my normal y equals sine of theta graph, that's the one in green, and multiplying all the y values by 3, because that gives me that vertical stretch that I was looking for. So this is y equals 3 times the sine of theta. If we now do that vertical reflection, that means flip all of the y values over the x-axis. So where I had a y value of +3, now it's going to be -3. Zeros don't flip. When I had -3, now that's going to be +3. So we're going down first, then up, and then back down. So this one is going to be the graph that we're actually looking for. That wasn't too bad. So this is y equals -3 times the sine of theta. So we're still using those same changes that we used all the way back in 1.5, those transformations. It's just on these sinusoidal graphs instead. Now, one thing that I would like to point out is what's called the amplitude, and that's the distance from the midline to the highest point. And I put midline in quotes because we haven't defined it yet, but I'm hoping you can understand that the midline is going to be the middle of the function where it averages out. So if I'm looking at, say, my regular old sine graph, the one in green, I oscillate between +1 and -1. So if I go right in the middle, that's at 0. So my amplitude is the distance between that midline and the highest point, which in that case was 1. If you look at the amplitude of 2 times the sine of theta, that was my purple graph, it oscillates between +2 and -2, so the middle of that is 0. If I go from the midline of 0 to the highest point, that's going to be 2. So that's what amplitude means, is the distance from the midline to the highest point. There's that definition of midline I was looking for. The center value of a sinusoidal function, which is the value that the function oscillates above and below, is called the midline value, and that happens to correspond to a vertical shift. Because as we saw with regular old sine and cosine, they oscillated around 0. So if we do a vertical shift, then that midline is going to move with it. So if we're looking at the function f of theta equals cosine of theta plus k, we know that the midline of cosine is 0, so that vertical shift of k is going to be our midline. So we're going to take a look at this graph and see if we can find the amplitude, the midline, and the period of the function. So let's see. I think it's going to be easiest to find the midline first. So we go up to 8 and down to -2. So we need to find out what's in the middle of those. One way you can do it is by adding the top and bottom values and dividing by 2, or really finding the average of them. So if I take -2 plus 8 divided by 2, that's 6 divided by 2, which is 3. That's my midline. We are going above and below that value. So my midline is at y equals 3. Now it shouldn't be too hard to find the amplitude, because the amplitude is the distance from the midline to the highest point. So that's going to be that height there. That's the distance from 3 to 8, and that's a height of 5. So my amplitude is 5. Finally, we want the period. The period is how frequently we repeat. So we need to find a point on our graph where we know the x value and find that point again when it repeats. Well, it looks like this point right here, x equals 0, y equals 3, that's a pretty easy point to track. Well, it happens again right here because notice I'm going up through that point. I'm going up through that point here. I'm going up through that point here. I'm going up through that point here. Well, I really only know the x value on that one. I have to kind of guess on these others. So it looks like we might need another point to work with. Aha! What if I look at this point here, the very top? I hit the very top again, here and here and here. Aha! So this point is negative pi over 2, comma 8. This point is positive 3 pi over 2, comma 8. So you might want to jump on the fact that it takes from negative pi over 2 to 3 pi over 2, which is a total distance of 4 pi over 2, which is 2 pi, to get from there to there. So it takes a full 2 pi to get 2 points that look nice. But in that time, how many full oscillations have I made? I've gone down and up once, twice, 3 times. So my period is 2 pi over 3. I am repeating this graph every 2 pi over 3 units. That's my angle. So again, the way I did that was I found 2 points on the same part of the graph. So I ended up looking at the highest part here, and I found those coordinates. The total distance x-wise between them is 4 pi over 2, which is 2 pi. But during that time, I made 3 full oscillations. So I have to divide that by 3 to get my period. So every 2 pi over 3, this whole function is repeating. We're going to use that information to look at a general form of sine and cosine. So given an equation in the form f of t equals a sine of bt plus k, or f of t equals a cosine of bt plus k, then the absolute value of a is the vertical stretch, and that vertical stretch is also known as our amplitude. The b value, so what's in front of t, that's going to be our horizontal stretch or compression, and it's related to the period by this equation here. You are going to want to know this one. Our period p is equal to 2 pi over b. So if you have the equation, then you take 2 pi divided by what's in front of your variable here, and that'll give you your period. And then k, as we saw before, is our vertical shift, and it gives us the midline. So we are going to determine the midline, the amplitude, and the period for the function f of t equals negative 4 times the cosine of 4t minus 1. I'm going to start with my midline because the midline is your vertical shift at the end. The midline is a horizontal line, so it will be y equals negative 1. Our amplitude is given by the absolute value of the number out front. So the absolute value of negative 4 is equal to positive 4. So the distance from the midline to the amplitude, or sorry, the midline to highest point is 4. Finally, we need our period. And our period is given by p equals 2 pi over b. And b is the coefficient in the parentheses. So our period p is going to be 2 pi over 4, and that reduces to pi over 2. Next up, I have a graph here that I'm looking at. I want to find a formula for this sinusoidal function. So let's see what we can do. It looks like my midline is going to be at -2 because I go from -4 to 0, and the average of those two is -2. So that's going to be my midline. Let me write that down. It was at y equals -2. Now I want to show you another Desmos picture because something we haven't talked about is when we're looking at a graph, how do we know whether it is sine or cosine? So taking a look at this picture here, it looks like when we go through the y-axis, we are at a y value of the midline, but we're going downward. So we're at our midline going downward. Let me show you this thing in Desmos. So here's what our sine graph looks like. When we are passing through the y-axis, we are at the midline going up. Well, in our graph that we were just looking at, we were at the midline but going down. So this might be a sine graph, but maybe a special one. For the cosine graph, when we're going through the y-axis, we're at our highest point. We definitely didn't see that. What about a negative sine graph? So this is the regular sine graph, but reflected vertically. This one, when we're going through the y-axis, we are at our midline going downward. This is the type of graph we're looking at. We are looking at a negative sine graph. And then just so you can see it, a negative cosine graph looks like cosine, but instead of starting at +1, we're starting at -1. So just to kind of reiterate, in the graph that we're looking at on the slide, it is a negative sine graph because at the y-axis, we are sitting on our midline, and as we go forward, we're moving down, we're decreasing. So let's see if that can help us. So we said this is a negative sine graph. All right, we still need our amplitude. The amplitude is the distance from the midline to the highest point. So that's going to be from -2 to 0. That's a height of 2. And then finally, we need the period, because remember, period P is equal to 2 pi over B. So if I'm trying to come up with the equation or the formula, I need my B value. So if I can find my period, how often I repeat, let's try looking at the peaks. So I have a peak at x equals -1 and a peak at x equals 3. So that's 4 units apart. So that means my period is 4. It only takes 1 cycle to do it, so I would divide it by 1, and that's just 4. So my period is 4, and we get 4 is equal to 2 pi over b. I need b for my formula, so I'll multiply both sides by b. 4b is equal to 2 pi. Dividing by 4, I get b is equal to 2 pi over 4, which reduces to pi over 2. Now, once upon a time, they gave us this formula written out. So let's see what this is going to look like. We're going to have f of t, or you could use y, it doesn't matter, we'll say f of t, is equal to our a value. We said our amplitude is 2, but it's a negative sine graph, so we'll put -2 times the sine of b times t. Our b value was pi over 2. And then we had t plus k, which is our midline. So we have -2. So this is the graph of f of t equals -2 times the sine of pi over 2t minus 2. Let's see if we can do an application with this. The Ferris wheel at the local fair has a diameter of about 85 feet, and it takes 6 minutes to complete a full rotation. Passengers board from a platform that is 7 feet above the ground. We're going to write an equation, for the rider's height above the ground over time. I'm going to draw a picture for this one because I think it's going to help. So passengers are on this little platform that's 7 feet tall. Then there's this Ferris wheel. Looks something like that. It's off the ground. Yay, Ferris wheel. We know that the diameter, so the distance across the whole thing, is 85 feet. And it takes 6 minutes to complete a full rotation. Looks like we have all the information we need there. So if you think about this, the passengers are going to start at 7 feet off the ground because you board the Ferris wheel from the bottom. So this is the lowest they're going to go. The highest they're going to go is going to be at the top of the Ferris wheel. The top of the Ferris wheel is 85 feet higher than what they started. So the highest is going to be the 7 feet that they started at plus the 85 feet that is the diameter of the Ferris wheel. And that gives us 92. So now we need to figure out where is the midline. The midline is given by the average of these two. So if we take the low point 7 plus the high point 92 and divide it by 2, that's 99 over 2, which is 49.5. That is our midline. Our amplitude is the distance from the midline to the highest point. So if I take my highest point, 92, and subtract my midline of 49.5, then we get that our amplitude is 42.5. And hopefully that makes sense because the amplitude is going to be half of the diameter. It's going to be the radius because that's going to be the distance from the midline to the top and then the midline to the bottom. So we have an amplitude, we have a midline, we need a period. They told us that it takes 6 minutes to get around the whole thing. So our period is 6. That's going to be equal to 2 pi over b. Multiplying both sides by b, then 6b equals 2 pi. And dividing by 6, we get b is equal to 2 pi over 6, which reduces to pi over 3. So we have the midline, we have the amplitude, we have the period, which gave us our b value. We just need to know whether this is a sine graph or a cosine graph, or a negative sine graph or a negative cosine graph. Keep in mind, we are starting at the bottom. We are starting at our lowest we are ever going to go. If you think back to the little Desmos graphs I showed you, starting at the very bottom, at the lowest valley, that is a negative cosine graph because we're starting at the lowest. So plugging everything in, we're going to have y equals, it's a negative cosine graph, so we'll have negative amplitude, 42.5. It's a cosine graph of b, which is pi over 3. and we were using t as our variable, plus our midline, and our midline was 49.5. At any given minute, this is going to tell you how high a passenger is off the ground. Now you may have noticed that sine and cosine look very similar. Because they are, there's just a horizontal shift in there. So we can do horizontal shifts of sine and cosine just like we could with our other graphs. So we're going to add one more tiny thing to the mix. Given an equation in the form f of t equals a times the sine of b times the quantity of t minus h plus k, or f of t equals a times the cosine of b times the quantity of t minus h plus k, that h value is the horizontal shift of the function. We're using h as our horizontal shift the way we have done in the past. So if we have t minus 4, then that's a shift to the right of 4. And if it's t plus 4, then that's a shift to the left of 4. So we are going to describe the graph of f of t equals 2 times the sine of pi over 2t minus pi over 4 plus 3 in terms of the original g of t equals sine of t graph. Something I need to point out is that in this form where we had the horizontal shift, the b value was factored out. That is important. If there is a value in front of t, you need to factor it out front. So if we take a look at this pi over 2t minus pi over 4, I need to factor pi over 2 out front and figure out what's left in parentheses. So definitely a t here, because pi over 2 times t gives me my pi over 2t. Then we have a minus sign. I need to figure out what goes here. So what we're asking ourselves is pi over 2 times what gives us pi over 4. To solve for what goes in that blank, I'm going to divide both sides by pi over 2, which is the same as multiplying both sides by 2 over pi. That'll leave me with this what that I'm trying to find is equal to, the pi's cancel out, 2 over 4, which is 1/2. I need a 1/2 right here. Another way to think about this is I am undistributing that pi over 2. So once I have my values in here, I need to make sure it matches the original. So pi over 2 times t is pi over 2t minus sign. Pi over 2 times 1/2 is definitely pi over 4. So that's right. I'm going to rewrite my original formula in this factored form. So we have f of t is equal to 2 times the sine of, we factored out pi over 2. It left us in parentheses with t minus 1/2 and then plus 3. So this 2 out front, that's our amplitude. That gives us a vertical stretch by a factor of 2, because the normal sine graph just had an amplitude of 1. We multiplied it by 2. This value is our horizontal stretch or compression. Pi over 2 is over 1. That sounds really weird. It's bigger than 1. So this is a horizontal compression by a factor of pi over 2. This one might be kind of confusing, but if you remember that period equals 2 pi over b, our b value was pi over 2. So our period is 2 pi over 2. If I keep change flip, that's 2 pi times 2 over pi, which is 4. The period is normally 2 pi, which is a bit bigger than 6. Now our period is 4, so it's gotten smaller. That's why it's a horizontal compression. We have a vertical shift because of the +3 right here. It moves it up 3. And finally, this -1/2 gives us a horizontal shift. And remember, this one's backwards of what you would think. You would think that would move it to the left. It actually moves it to the right by 1/2. All right, one more. We're going to find a formula for the function graphed below. I'm going to start by writing a very generic form of this. We had y is equal to a times the sine or cosine, I'll just use sine for now, I guess, of b times t minus h plus k. Now, when I look at this graph, I need to determine whether it's sine or cosine, negative sine, negative cosine. I'm going to start doing that by finding my midline. I know that sounds kind of weird, but this is oscillating between +6 and 0, which puts my midline at 3. My midline is y equals 3. My amplitude, the distance from the midline to the top, is 3. So my a value will be 3. Now you need to decide for yourself, do you see this as a sine graph or a cosine graph? You might be like, well, how do I decide? Sine graphs start at their midline and increase from there. So if you're thinking of your sine graph starting here, that's definitely a sine graph. You could also think of this as cosine, because if you think of it as a cosine graph, then you're starting at your highest point. So you could think of it as here. I'll do it both ways just so you can see both. So if we think of this as a sine graph, then we're going to stick with this guy. We have our y value, which is our midline, which is k in there. We have our a value. We need our b, which is related to our period, because period p is equal to 2 pi over b. And it looks like we're repeating from 1 until 9, so that's 8 units apart. Our period is 8. So 8 is equal to 2 pi over b. Multiply both sides by b, we get 8b equals 2 pi. Divide by 8, and we get b is equal to 2 pi over 8, which reduces to pi over 4. Last thing is that horizontal shift. If we're thinking of this in terms of sine, then we need to start when we're at our midline and increasing. That's a horizontal shift of -1. So we need to shift to the left, -1. What that means is if we are thinking of this as a sine graph, we are getting y equals our a value 3 times the sine of our b value, pi over 4, times in parentheses t minus a -1, which is t plus 1, plus our midline of 3. If you graph y equals 3 times the sine of pi over 4 times t plus 1 plus 3, you get this graph. I personally don't see it that way. I like cosine. I'm not sure why, because I see this as my starting point. I'm at the top of a hill. I know where that is. All of my values stay the same except for my horizontal shift. If I'm thinking of this as cosine, then I am starting 1 to the right from our normal spot, so I need a horizontal shift to the right of 1. Everything else stays the same. So we would have y equals a times the, whoops, we know what a is. A is 3, times the cosine of our b value, pi over 4, times t minus 1, because that moves us to the right one, plus 3. These two equations graph the exact same. So it's all a matter of how you see it. If you have questions about this, let me know. I know it's kind of weird that there are multiple right answers, but in this case, there definitely are.